In this lesson, we'll set up the math for cross-correlation again and discuss some terms and simplifications that we'll make in order to compute the backwards pass for a convolution layer. It's instructive to calculate the backwards pass of a convolution layer, even though in practice, automatic differentiation will do it for us. Similar to the fully connected layer, we'll end up at the end with a simple vectorized linear algebra operation that can be implemented efficiently in graphics processing units. We'll also see an interesting duality between the forwards and backwards passes as it relates to the cross-correlation and convolution operation. As a reminder, here's the cross-correlation operation. Specifically, we'll have a kernel that's shown in the middle here, a 3x3 kernel, that is strided across the image on the left, and this produces the corresponding output map on the right. If you remember, we start with a coordinate system on the upper left being 0, 0 in the image, and the kernel as well as the output map. Each output pixel specifically gets contributed to by an input pixel multiplied by some element of the kernel. Let's take a look at the equation in a little bit more detail. The double summation is iterating across the kernel. And so we can define these iterators A and B that go from top to bottom and left to right, starting from the upper left pixel 0, 0 and moving down to the lower right. Similarly, we can have iterators across the output map. Specifically, this entire equation is showing how to calculate the output y of r comma c. However, in general, we want to calculate all of the outputs. And so we have these iterators r and c that again go from top to bottom and left to right. Now we're going to make a bunch of simplifications just to derive the gradients. This does not lose any generality because we can always actually extend it to more complicated settings, but in order to derive it, it's much easier to do it this way. It'll make our life a lot easier. Specifically, we're going to assume that we're going to have one channel input. That is, we're not doing RGB. It's just a grayscale image, for example. We're just going to have one kernel. And so what is the output size going to be on the output map depth? It'll only have a depth of 1. We're also going to add padding, and here it's going to be a little bit different than how we showed padding previously. We're not going to center the image across the padding. We're going to add padding to the right and to the bottom in order to make the output size the same. That way we can use the iterators R and C also on the input. Let's start by defining some things. The output map, Y, is going to be height by width. This is the same size as the input. And the reason this is true is because we added padding at the input in order to make the output the same size. And so the upstream gradient, the partial derivative of the loss with respect to our output for this convolution layer, is given by whatever layer is after this one. And we're going to assume some things about it. Specifically, it'll be height by width. And then again, this is because we added padding. And you'll notice a small change in the convention in terms of the partial derivative of the loss is scalar with respect to y, a matrix. Again, this is just to make our life easier. We'll also use this notation in order to access one particular pixel of the Jacobian. That is, we'll want the partial derivative of the loss with respect to one pixel in our output y. We'll have similar accessor mechanisms for the input as well as the kernel. Just like any other layer, we'll define the convolution layer as some black box that has an input, an output, and a set of parameters. Specifically, it has an input HL-1, typically some tensor, an output H of L, where again the depth is equal to the number of kernels in this layer, and W, the learnable parameters. In this case, the parameters are the kernel values themselves. And we'll again want to perform these various calculations. We want to compute the partial derivative of the loss with respect to our input, HL-1. And we'll want to compute the partial derivative of the loss with respect to our weights, that is the kernel values, in order to update them. And we'll want to do this based on the upstream gradient that we're given from whatever module exists after this one. That is the partial derivative of the loss with respect to our output. This is something we're given. And if you remember, we'll use the chain rule to compute this. The partial derivative of the loss with respect to our input will just be equal to the partial derivative of the loss with respect to our output times the partial derivative of the output with respect to our input. Again, this is saying that if we know how the loss changes as our output changes in small ways, and we know how our output changes if our input changes in small ways, then we can multiply those contributions and get the ultimate change of the loss with respect to our inputs. Similarly, the partial derivative of the loss with respect to our weights, again, uses this chain rule. And so we'll go through each of these two different terms and show you how we can derive them. In this lesson, we'll derive the gradients for the convolution layer and show how interesting characteristics derive from it and how it can be implemented efficiently, just like any other layer, using linear algebra operations. Let's start with the gradient for the weight update. Specifically, we can do this one pixel at a time. That is the partial derivative of the loss with respect to WA comma B. For example, we can pick 0, 0 in the kernel. Again, this is one pixel in that middle kernel that's 3 by 3 matrix. And so we can try to ask ourselves the following question. What does this weight affect at the output? Because if you remember, the forward pass induces a computation graph where this particular pixel, W of 0, 0, this weight, performs some effect on the output. And this can be multiple outputs. You can see it as multiple edges coming from this pixel in the kernel to the output map. And so for each edge that's outgoing from this pixel, we want to have a corresponding backwards edge through which gradients flow. And so what do you think this weight affects at the output? Which of the pixels in the output does it affect? The answer is everything. This is because we're striding the kernel across the input image. So in the first location, that first pixel in the input, x of 0, 0, is multiplied by w of 0, 0. And that gets summed with the other contributions to result in that output map, y of 0, 0. But then we move the kernel over one spot. And again, it's weight shared. We're using that same weight. And so there's another outgoing edge where now we're multiplying w of 0, 0 with x of 0, 1. And that gets contributed to the output of y 0, 1, and so on. As we continue to do this, if you think about it, that one kernel pixel is affecting the entire output. If we change that one kernel pixel, it'll actually change the entire output map, at least by a little bit. And so because this one kernel value affects all of the pixels on the output, we actually need to incorporate all of the upstream gradients. That is, partial derivative of loss with respect to y of 0, 0, 0, 1, and so on, all the way to the end. And the way we can do this is through the chain rule. Again, if you have an outgoing arrow in the computation graph from a particular variable, that is, that variable affects multiple things at the output, then we'll just sum the gradients when we perform the backwards pass. That is, you'll have a corresponding backwards edge back to the same variable, and you'll add all the gradients across all the edges. And so this is what it looks like. We'll have the partial derivative of the loss with respect to w of a prime b prime is equal to the summation across the entire output map. And for each pixel, we'll use the chain rule locally. We'll do the partial derivative of the loss with respect to that pixel. And again, this is given to us as an upstream gradient times the partial derivative of the output pixel with respect to this particular weight. And so again, what we're doing is summing over all output pixels and performing the chain rule locally within that. We're multiplying the upstream gradient, which is known, times some value that we need to compute. And so this is really the only term that we need to compute. The partial derivative of our output pixel, r comma c, with respect to our weight or kernel, a prime comma b prime. Now, what will this look like? You can do this actually visually or analytically. In this case, let's do it visually. On the bottom, you can actually see that when we have a pixel r comma c at the output, and we're applying a particular kernel, pixel a prime comma b prime, then actually there's a question of what is the input pixel that is multiplied by it? And if a prime comma b prime is 0, 0, then it's the input pixel r comma c. Again, this is just because the way we define the operation, and when we stride the kernel, this is the kernel position that corresponds to the output pixel r comma c. That is, the kernel pixel 0, 0 is multiplied by the input pixel r comma c. And so when we actually have the kernel pixel a prime comma b prime, which input pixel is multiplied by it? the reason we want to know this is we're trying to take the derivative. And again, the derivative of this w times x dot product is just the particular elements of x that are multiplied by the kernel pixel a prime comma b prime. And if you look here, the arrow gives it away. It's actually x of r plus a prime comma c plus b prime. And so again, when we're looking at the output pixel r comma c and a particular arbitrary kernel pixel a prime comma b prime, the actual input pixel, which it gets multiplied by, and hence is the derivative, is x of r plus a prime comma c plus b prime. Again, one way to easily do this is just think of the extremes. When a prime and b prime are both 0, then we just get x of r comma c, which is visually what is depicted here. If we move it 1 to the right and 1 down, then we get r plus 1 comma c plus 1, and so on. And so that's it. That's our gradient for the partial derivative of the output pixel r comma c with respect to the kernel pixel or weight a prime comma b prime. And so let's plug this in to the original equation we had. Remember, this is just the derivative for a prime comma b prime for this one particular kernel location. If we move or stride the kernel across the image, we need to sum up the gradients across the entire output image. And so that's what this equation is doing. And so we have just the summation over all output pixels of the chain rule, the partial derivative of the loss with respect to output pixel r comma c times x of r plus a prime comma c plus b prime. And so one thing is you can look at this equation and maybe be reminded of something that we learned about before. In other words, what does this equation actually look like it's implementing? And if you think about it, it's actually just a cross correlation. It's the cross correlation between the upstream gradient, partial derivative of the loss with respect to the output, and the input. And we do this particular cross correlation between the upstream gradient on the output and the input until we get k1 by k2 values. And then that is our gradient. This highlights it a little bit better. In the forward path, we're striding this kernel across the image. And we have some particular kernel value that we care about, a prime comma b prime. And we want to compute the backward pass for that. When a prime comma b prime is 0, 0, this is showing the cross correlation that we'll be doing. We're actually just cross correlating literally the input and the upstream gradient, partial derivative of the loss with respect to our output, which again will be a matrix of size h by w. For the backward pass of k of 2 comma 2, this is showing what we're cross correlating. Again, if you remember, we're padding the input. And so we're going to cross correlate the partial derivative of the loss with respect to our output, which is this matrix, and the input, but offset. And so essentially, this is what we're doing. We're just striding the upstream gradient across the input, and we're going to do it for the size of the kernel, and that will be our gradient. Now that we have the gradients with respect to our weights, let's calculate the gradients with respect to our inputs. Again, the reason we need this is not to update the weights for this layer, but to pass back to whatever previous layer occurred before this one. And so again, what we want to do is let's calculate this one pixel at a time, the partial derivative of the loss with respect to our input pixel, r prime, comma, c prime. And again, we can try to think, what does this input pixel affect at the output? What do you think it is? Again, if you think about it and visualize striding the kernel around the input, the image, producing the output, what you'll notice is that there's several positions where the particular kernel touches this pixel. And whenever the kernel touches the pixel, that means that the pixel gets incorporated into the output through the summation. And that means that if I change this particular input pixel, then the output pixel will change, which means that there should be a gradient. And so I can try to reason about what the neighborhood is that is affected at the output. This is because I need to chain rule it with the partial derivative of the loss with respect to that particular output pixel. And so I can try thinking about all the different positions that this pixel affects at the output. And so if you think about it, you can try to visualize all the places where the kernel can be that touches this pixel. So this shows the four extremes of that. On the upper left, that is position 1. That is the kernel position where the lower right of the kernel is touching that pixel. Similarly, in position 2, the lower left of the kernel is touching the pixel r prime, comma c prime. Again, the reason we care about this is if the kernel is touching this pixel, that means that pixel is multiplied by a particular kernel value and gets added to the output value. Position 3 and position 4 again are the same, except they're the extremes on the bottom side. And so we can try to reason at these 4 extremes and the input side. Which parts of the output does it touch? The reason we care about this is we're applying the chain rule and we need to know which elements of the upstream gradient that we get should we actually use in the chain rule. And if you work it out, this is what it looks like. The 4 extreme points on the input correspond to these 4 extreme points on the output. That is point 4, which is where the kernel position 0, 0 touches r prime, c prime. It actually corresponds to r prime, c prime on the output side. And so again, these are the 4 points on the output where the corresponding locations are for this particular input pixel, r prime, c prime. Now that we know all the positions on the output map that are affected, we can compute the chain rule. That is, we can compute the partial derivative of the loss with respect to this particular input pixel, r prime, c prime, as the summation of all the affected pixels on the output and sum all the chain rules. That is, partial derivative of the loss with respect to y of the affected pixel times partial derivative of the affected pixel at the output with respect to this particular input pixel, r prime, c prime. Again, the reason we're summing up all the gradients is because you can see this as a computation graph, where this particular pixel in the input, r prime, c prime, has an outgoing edge to multiple output pixels. And so for each of those output pixels, we want to calculate its effect and calculate the backwards gradient going through that edge. And so we can try to figure out what should these actual pixels be. And so this shows the particular pixels that are affected on the output. Specifically, if you think about it, when you have kernel pixel a, b equal to 0, 0, then you have the output pixel y of r prime, c prime. That is, when the input pixel r prime, c prime touches the kernel pixel 0, 0, that kernel is all the way to the right and all the way to the bottom. And so that corresponds to position 4. Similarly, when the kernel is all the way to the upper left, that means you're multiplying the input pixel r prime, c prime times the lower right of the kernel. And so that's why you subtract r prime minus a and c prime minus b. And so this is the final chain rule or set of chain rules that we're going to sum in order to compute the gradient with respect to this particular input pixel. Again, the partial derivative of L with respect to y of r prime minus a, c prime minus b is given to us. We're given that entire matrix or Jacobian. And so all we need to compute is the right side. Partial derivative of y of r prime minus a, c prime minus b with respect to this input pixel, x of r prime minus c prime. This time, we'll do this analytically with the definition of cross-correlation again. But in this case, we're going to use different variables a prime and b prime. The reason is that we've already defined a and b as iterators over the kernel in the previous slide, so you want to distinguish it from that. And we can plug in the actual pixel that we wanted. We didn't want r prime and c prime. We wanted r prime minus a and c prime minus b. So if we use those pixels instead, then this is what we get. Again, this just comes from the definition of cross-correlation. And so we want to compute the partial derivative of y of this pixel r prime minus a, c prime minus b with respect to the input pixel x of r prime, c prime. So what do you think that comes out to? That is, which of these terms in the double summation actually touch this pixel x of r prime, c prime? Because all the other terms that touch different input pixels don't matter. And so it turns out it's just the kernel of a, b. The reason is that we want the term with x of r prime, c prime in it. And this happens when a equals to a prime and b equals to b prime. And so now we can just plug into the earlier equation that we had. That is, we summed over all affected output pixels. And for each affected pixel, perform the chain rule. And if we do that, this is what we get. And again, this might look familiar to you. This is actually just a convolution between the upstream gradient and the kernel. And so this can again be implemented efficiently. Rather than performing the convolution, we can actually just perform cross correlation. But we need to flip the kernel here. And so we can just implement the kernel flipping and cross correlation. And all of these operations can be implemented via matrix multiplication, same as the fully connected layer. And so again, we've derived both aspects of the gradient for the convolution layer. There's lots of indexing and it's a little bit confusing, so you should go through it to make sure that you understand it. But in the end, we get very simple operations and we get a nice duality where if we perform cross correlation in the forward path, then the particular gradient with respect to the input is actually a convolution, which is pretty interesting. Now that we have many different types of layers under our belt, that is fully connected layers, pooling layers, and convolution layers, as well as nonlinearities, we can start building very complex functions like building blocks. And so in this lesson, we'll talk about simple convolutional neural networks, which alternate different layers of these types. Since the output of convolution and pooling layers are multi-channel images or tensors, we can actually sequence them just as any other layer. That is, the input will be some width and height and depth. And if we are using a number of samples in a mini batch, then the number of batch elements. And the output will be the same, perhaps a slightly different height and width or a different depth, but still the same shape tensor. And so we can, for example, take an image, perform a convolution layer on it, which has a certain number of kernels of the depths that the image has. So for example, RGB, which is depth of 3. And the output of that convolution layer will have the depth equal to the number of kernels, and the width and height can be either the same if we pad the input image or slightly smaller if not. And then we can perform pooling operation, for example, max pooling, and then again get the same shape tensor, except we might have a smaller width and height, for example. And then again, we can just continue to iterate or alternate across these different types of layers. Here's a depiction of a simple convolutional neural network that you can design. You have a particular input image, you have one convolution layer, and typically we add nonlinearities because again, convolutions are just linear operations, and we can't really alternate linear operations because it doesn't really give us any additional representational power. And so we'll have the output of the convolution layer be fed through an element-wise nonlinearity, and then we'll perform pooling to downsample. And then we'll apply another convolution layer, again with some nonlinearity after that. And at the end of this, we'll have a set of much smaller features. They're still spatially relevant, and they're not converted into vectors as they are in fully connected layers. But they're useful, much lower dimensional features that if we optimize to reduce some loss, will hopefully represent more abstract features the deeper we go in this neural network. And typically, we'll take these last feature maps and feed them through several fully connected layers. And these again can be seen as just the classifiers. The hidden parts of this fully connected layer will again extract some hopefully high-level abstract meaningful representations that are much lower dimensional again than the input image. And then we'll feed it to some last fully connected layer that has the number of nodes equal to the number of classes that we have. And we'll convert the outputs of those nodes, which can be considered as scores, into probabilities using softmax and feed it through a cross-entropy loss, for example. And so now we have an end-to-end convolutional neural network that starts from a raw image, progressively extracts more and more abstract and meaningful feature representations, feeds it through some deep, fully connected neural network, and then outputs some set of predictions. And through the loss, we'll be able to optimize the entire chain here through backpropagation. We'll start at the loss, feedback gradients, update the weights for the fully connected layers, push the gradients back through to the convolution layers, update the kernels, push it through the pooling layers, which don't have parameters but will send back gradients to the inputs, and then push it again through the convolution layers to update the kernels there, all the way to the image, which of course we don't really need to update. And so again, we can just optimize this entire chain of transformations in an end-to-end manner where we're optimizing the best kernels that we can possibly find in order to minimize the loss at all stages, as well as optimizing the weights in the hidden layers as well. This is called a convolutional neural network. One interesting aspect of alternating these types of layers is that you'll have an increasing receptive field for a particular pixel deep inside the network. Again, the receptive field defines what set of input pixels in the original image affect the value of this node or activation deep inside the network. If you see the depiction here, a particular pixel in the output map in the last convolution layer here is affected by a small window around it in the previous layer. But each of those pixels in the small window are affected by some window around it in the previous layer before that. And you can keep going back over and over. And as you can see, the window gets bigger and bigger and bigger. And so as you get deeper and deeper into the neural network, as you perform more convolution layers and pooling as well, you'll see that this receptive field continues to increase over and over again until you get a pretty large influence in terms of the actual input image with respect to a particular pixel deep inside the network. This will be important later when we start designing interesting convolutional neural network architecture. Just a bit about how people typically depict convolutional neural networks. You'll see these types of diagrams quite frequently, either in conference papers or in blogs and so on. You'll see, for example, on the upper left, these 3D convolution neural networks where you have progressively smaller image sizes, sort of like a 3D trapezoid. And then you'll see these two, for example, fully connected layers, which are typically depicted as 3D vectors. Or you can have a 2D depiction as well, where you just have a 2D trapezoid, and that feeds into two fully connected layers. Again, as we'll get more and more complex neural networks, we'll want to depict them in visually simple ways so that you can immediately understand what the architecture looks like. And so we have finally gotten to the point where we can now understand convolutional neural networks as they existed since the 1980s. Again, these have been processing bank checks, for example, to perform optical character recognition for quite a while now. And so what you can see here is that these architectures are very simple and similar to what I've shown in previous slides. You have an input image, in this case a 32 by 32 image, and you have that being fed into a convolution layer. In this case, you have 6 kernels, and so the output is 6 28 by 28 output maps or feature maps. Now we downsample those. In this case, it's called subsampling, but it's just a max pooling layer. And so we get 14 by 14 output maps. We perform another convolution layer. And again, we get here 10 by 10 maps. In this case, we'll have 16 kernels. And this is going to be a similar trend to other neural network architectures where we'll have increasing numbers of kernels as we get deeper into the network. And then we have another subsampling layer. And finally, we'll end up with very tiny maps. We'll have 16 5 by 5 feature maps. And again, we're hoping that these 5 by 5 feature maps represent more abstract features. For example, strokes or shapes in the input image. And so now these feature maps are small enough that we can feed them into fully connected layers. We don't have to worry that much about a large number of parameters. And in this case, we'll have 2 hidden layers and 1 output layer. In this case of size 10, because that's the number of output categories. If you notice here at the end, it says there are Gaussian connections. And actually that just corresponds to a mean squared error loss function. This was back then when we didn't use cross entropy, for example. These days, rather than mean squared error, we use cross entropy. And so now we can start looking at understanding what are these networks learning when we feed them a bunch of images and optimize the kernels and the fully connected layers. Here we're going to look at handwriting and specifically hand digit recognition. And so we'll have digits from 0 to 9, and at the output we'll have a fully connected layer with 10 outputs. And in between we'll have a series of convolution layers as well as fully connected. And we could try to visualize various things. In this case, we can visualize the actual output maps themselves. That is, when we stride a kernel across the image, we'll have an activation map that'll show high values where the particular feature exists on the image. And so we can try to visualize those output maps. And that's what this is visualizing in the intermediate layers. We can also visualize the fully connected layers, but as you notice, they kind of destroy spatial information, and so it's a little bit harder to interpret. And so we can look at various features that we talked about. For example, we mentioned that convolution operations have this property of equivariance. That is, when you move the input in particular ways across the image, the features also move. That is, the feature detections in the output maps also move in the same way as you move the input. And you could see this in the intermediate layers. You can also see invariance at the final outputs. That is, even if you move or translate the digit across the image, it will still output that it's a 4. We can also have some rotation invariance. Again, this is not as strong as the translation invariance, and you can try to enforce this a little bit more by adding rotated digits inside the training set as well in a data augmentation form. But here you could see that there's some rotation that the network is invariant to, and at some point, if you rotate it too much, then it stops predicting that it's a 4. This is, for example, likely because the convolution kernels, for example, might detect edges of particular orientations, and obviously those orientations change as you rotate the image. We can also have some form of scale invariance where making the digit smaller or larger still results in the network predicting 4s, which is what it's printing on the top. And so now we've come to a point where we can have these very generic building blocks and just design arbitrarily complex convolutional or other neural networks. Again, the only thing limiting what we can use is aspects such as memory, computation, or our ability to optimize. That is, if we make the networks too complex or too deep, it could be that our optimization methods are too simple and can't really find good local minima. And that actually indeed turns out to be the case, and we can then make some architectural or other changes in order to fix that. And so now we get to the fun part of the course where we can just explore the space of architectures and show which ones produce state-of-the-art results across various applications, including computer vision and image processing. And later we'll talk about things like natural language processing as well. In this lecture, we'll talk about advanced convolutional neural network architecture. That is, advanced modifications that we can perform when we design different types of neural networks in order to get state-of-the-art results across large-scale applications such as computer vision. One of the key things that was required to show the true power of deep learning is large-scale benchmarks. In the past, small data sets just did not have enough data to fit very complex functions. Yet the real world consists of very complex things. That is, the function mapping from images in natural world to class labels is actually pretty complex. If you have a very tiny convolutional neural network to try to perform that mapping, you'll probably not be successful. If you have a very large convolutional neural network, then it has enough capacity in order to model that function. But fitting all those parameters requires a lot of data. And so this is why deep learning came onto the stage again around 2012. It was entered in a particular competition called ImageNet that had over 1.2 million labeled examples of images where you had each image fitting into one of 1,000 different categories. These categories included many different dog and cat species, but also random objects such as keyboards and mice and so on. And so on the bottom, you can see the plot of improvement happening across the years in this benchmark. On the y-axis, you could see the top one accuracy. That is, you have to get the correct answer in your top one prediction. So you can take your argmax over your probability distribution over the classes, and that is your prediction, and that has to be correct. And around 2012 is when deep learning was employed for this, and it completely blew the existing methods out of the water. It performed much, much better than all of the hand-coded, hand-engineered feature representations that were then fed into various machine learning classifiers such as support vector machine, and so on. And as you can see, this was only the tip of the iceberg. better neural network architectures kept coming about, better optimization methods, better regularization, and data augmentation techniques all led to progressive improvements such that the accuracy now is above 80% for a very complex dataset. So we can take a look at some of the dominant convolutional neural network architectures that have performed really well on this benchmark task. Again, the space of possible convolutional neural network architectures and optimization algorithms and loss functions and regularizations is very large and, in fact, infinite. And so we can't really cover all of them. We'll just cover the major ones that dominated the scene. The first architecture that performed really well, again introduced in 2012, is the AlexNet architecture. This shows again a depiction of the convolutional neural network architecture. One thing that might be a little bit strange is that you can see this horizontal split, and that's only because this neural network architecture was so large that it could not fit into one graphics processing unit, and so it was split into two. And so what you can see is, again, similar to what we have seen before. You have an input image, in this case, step 3. You have a particular convolution operation or convolution layer here of size 11 by 11, performed with a stride of 4. And then you have max pooling layers and additional convolution layers and max pooling layers and so on, all the way to a fully connected layer at the end that leads to output nodes that have 1,000 dimensionality, since there are 1,000 classes. Let's take a look more detail of each layer. Here we can see each layer laid out in terms of its dimensionality. Specifically, the input here was 227 by 227, which is the width and height of the image, by 3, which is the depth of the image. We then performed convolution layer with 96 11 by 11 kernels at stride 4 with no padding. What you notice is that in the beginning, very large convolution were done. The window size 11 by 11 is pretty large. And this was done because, again, memory was an issue. These days, the kernels that you'll see are much smaller. And so you can try to reason about how many parameters this convolution layer has. So how many do you think conv1 layer has? In this case, because you have 11 by 11 filters and you have 96 of them, you'll have 96 times 11 times 11 times 3, because again, all of these filters have a depth of whatever input that they're taking, plus some bias terms. Then we have a pooling layer. In this case, it'll be 3 by 3 max pooling at a stride of 2, and you'll see that the output is 27 by 27 by 96. Again, the depth does not change. We're only changing the width and height. Then there are some specialized normalization layers that I won't discuss because they're actually not common anymore. There's another convolution layer. Here we have 256 5 by 5 filters at stride 1, padding 2. And as you notice again, as I mentioned, the number of kernels that we use actually tends to increase as we get deeper into the neural network. One reason for that is the sizes are actually getting smaller and smaller. And so because your filter sizes will be smaller, you'll actually be able to not increase the number of parameters too much by having many kernels. Then there's another max pooling layer. Again, here it's 3 by 3 that results into a 13 by 13 by 256 output. We'll have another normalization layer, and then several more convolution layers in sequence, and then finally a max pooling layer. And here at this point, we have very tiny feature maps. We'll have 6 by 6 by 256 outputs, and we'll actually just have fully connected layers after that. So we have two hidden layers, FC6 and FC7, and an output layer that has 1,000 nodes because that's how many classes we have in the dataset. And so there are several key aspects that were really important to getting this network to perform really well. This was the first network architecture that used the rectified linear unit instead of sigmoid. Again, sigmoid was extremely popular, or tanh in some cases, but they have some properties that were not very good for optimization. They had specialized normalization layers, although these days we don't use that anymore. They actually used PCA-based data augmentation. So PCA is principal component analysis, and you can use it to actually, for example, model different lighting conditions, because lighting actually tends to produce the most variance in your data. And so that's an interesting form of data augmentation. Again, it's a little bit computationally heavy and not done anymore. This was, again, the first network to use dropout as a regularization. And again, because there are so many parameters here and such capacity for the network, we do want to heavily regularize it to prevent overfitting. And finally, in order to eke out those last few percentage points, there were 7 neural networks, all initialized randomly and trained to convergence, and then their predictions were combined in some way, for example, by weighting the probabilities and summing them together. Subsequent to the initial success of AlexNet, lots of new architectures were designed. And often these architectures had various interesting changes, but also just went deeper, that is, added more and more convolution and pooling and other types of layers. This depicts the VGG neural network architecture that was very popular for a while. And as you can see, there's actually different variants of it depicted by different letters. One of the key interesting things about VGG is that it used the notion of repeating particular blocks of layers. That is, we can have, for example, convolution layers 3 by 3 that are in sequence, and this represents a module, and then we can just alternate that module in a sequence. And so you can see here different depths of networks had different types of modules that are repeated over and over again. And again, the more layers you had, typically the more parameters you have at the end as well. So this shows one particular variant, and here again the input is 224 by 224 by 3. There's a series of convolution layers. Here conv3 means 3 by 3 convolutions, and then we have pooling layers occasionally interspersed. One thing to notice is that all the convolutions are 3 by 3, unlike the larger convolutions that were made earlier in AlexNet. And again, one of the key factors here is that due to the increasing receptive field, the deeper you get into a neural network, you can actually not use those large convolutions, which aren't that efficient because they have a lot of parameters. 11 by 11 convolutions have a lot more parameters than 3 by 3 convolutions. And so here, we're just repeating 3 by 3 convolutions, except that we're going to make it deeper. And then at the end, we still have a good receptive field. That is, deep inside the network, the last convolutional output map actually has a high receptive field that looks at most of the image in the original input. And so again, at the end, you have a pooling layer and multiple fully connected layers and so on. One thing to note is that you have most of the memory usage occurring in the convolution layer. Why do you think that is? If you remember, in order to produce the gradient in the backwards pass, you have to store the activation that you obtain during the forward pass. This is because the gradients are functions of those forward pass activations. And so if you think about it, a convolutional layer has a very large output. For example, if you're given an input image 256 by 256, the output is close to that, except that the depth is the number of kernels. So if you're using 256 kernels, you have 200 by 200 roughly times 256 size tensor, which represents a large memory footprint. On the other hand, most of the parameters are in the fully connected layer. The convolution layers don't have that many parameters because the 3 by 3 convolutions just have that many 3 by 3 by the depth of input plus some bias terms, number of parameters. The fully connected layers, on the other hand, have the input dimensionality times the output dimensionality. So in this case, you could see that the first fully connected layer has 7 times 7 times 512, which is the size of the input, times 4096, which is the size of the output. And that's how many parameters you roughly have. Of course, there's some bias terms as well. And that represents 102 million parameters just for one fully connected layer. So again, the fully connected layers are very parameter heavy. And this has a lot of implications for, how much data you'll need to fit those parameters and so on. Some of the key aspects of the VGG network, again, are that there are repeated blocks, and these repeated blocks have 3 by 3 convolutions with small strides. If you notice, AlexNet had very large strides, but you're kind of losing information if you do that. And so here they were able to afford larger strides. Some of this came due to better computational platforms, that is, better graphics processing units came out. 2 by 2 max pooling layers were also used, and the end result had a large number of parameters. For example, in this case, we had hundreds of millions of parameters, unlike about 60 to 70 million parameters for AlexNet. And so here we almost doubled the number of parameters. However, as you can see in the chart in the previous slides, the performance is much better. And so in subsequent years, even deeper networks were developed. This shows the inception architecture, which again, you can tell has repeated blocks that are repeated over and over again to form the neural network. And each of these blocks are composed of simple layers that we have already learned about: the fully connected layer, convolution layer, max pooling layers, and softmax activation layers to feed cross entropy. And these modules had several interesting aspects to them. First, they used parallel filters, that is, filters of different sizes in parallel, so that you can get features at multiple scales. For example, if you have small edges or large object parts within the same layer, you can pick them up. They also had these smaller filters, such as one-by-one convolutions, that we'll talk about later. And so you can manipulate the sizes of all these, including padding and so on, so that the output sizes in terms of width and height are all the same. And then you can perform a filter-wise concatenation. That is, if one of these blocks output a particular width by height by 100 and another block outputs width by height by 50, then at the end you concatenate them and then you'll have a depth of 150. And again, the key idea here is we want to pick up complex features at multiple scales, all in the same layer. One of the downsides is that this increases computational complexity. It doesn't really add a lot of parameters, but you are performing 4 times, for example, the number of computations than if you just had a single convolution layer here. Eventually, as the depth of the neural networks increased, the ability to optimize them became a bottleneck. That is, as we increased the depth, we actually obtained higher error. So here you could see the 56-layer neural network had a higher error on these different data sets. And so researchers investigated why that was the case. And it turns out a simple modification you can make to these network architectures is to add what's called a skip or residual connection. That is, you can see here a path that goes from the input x through some set of transformations, some weight layers, and for example, a ReLU, and that transformation is added to the identity function. That is, rather than having to output a completely new thing given the input, you're just adding residual elements to the original input. That is, you're just optimizing the weights such that you make small changes to the input rather than each layer having to output something completely new. And it turns out this is easier to learn, and there's some theory here that you can show, for example, that there's better gradient flow. Again, gradient flow is one of the key things that one can look at in terms of making sure that learning is occurring properly. And you can actually show that these skip connections allow learning to occur much more effectively. You can actually show that any particular layer can transfer its output to any other layer subsequently in the neural network in identity, that is, without transforming it. This is because, for example, it can learn in the weight layers to not perform any transformation, or for particular types of inputs, it can learn weights that make the transformation zero. And so this is actually also true in terms of gradients. That is, during the backwards pass, you can pass the original gradients from any particular layer to any other layer. And so again, the neural network can learn to essentially have good behavior in terms of the forward and the backwards propagation of information. And so you can take these particular modules and again repeat them over and over again. And so on the left, you can see various different types of modules. You can see a 34-layer plain neural network, but a 34-layer residual neural network. And there's nothing special about 34. You can have any number of arbitrary layers here. And one of the key things is that adding these skip connections can actually allow you to optimize these deep networks. So the winning entry that used residual networks, for example, used 152 layers. And in some cases, people have used even more as well. Another interesting development is that we can actually explore the space of possible architectures, and in many cases, just modules that we repeat over and over again, using learning methods as well. For example, you can use evolutionary learning or reinforcement learning, which we'll learn about later, in order to explore the space in a more intelligent way than just random. We can also learn very densely connected deep neural networks, and then prune connections that we may not need in order to perform automated neural network connectivity learning. And again, typically, we don't perform this over large neural networks. We just learn the building blocks that we then repeat over and over again. And we can even parameterize how we repeat these blocks. And so using these automated methods, we can actually, in some cases, beat human designed neural network architecture. One thing to note is that often some of these neural network architectures have some difficult properties in terms of optimization. So not all of them are as easy to optimize. Residual neural networks, for example, are well known to be very easy to optimize, whereas some of these evolved architectures require a lot more tuning. And one of the key things that is important now is not just increasing the depth and number of parameters, but actually the reverse. How can we get the same performance by reducing the number of parameters? And so over time, people have designed different types of architectures that actually get even better performance, but are much more efficient. So again, different evolved architectures, such as what's called efficient net, have been designed, and these networks perform really well as not have a lot of parameters. And again, you can see the sheer pace of progress that has gone from a top one performance of around 55% for AlexNet all the way up to 80 plus percent on a very challenging data set that has 1,000 categories. And so now we'll start exploring some of the more interesting things that you can do with convolutional neural networks as well as other types of architecture. Because we can not just add depth, but we can also add, for example, additional loss functions or additional types of layers that are specific to different types of domains that really increase the performance across a wide range of applications. In this lesson, we'll talk about generalization. That is, how can we generalize from the training set to the test set, as well as transfer learning, which can significantly reduce the amount of label data that we need to fit the large number of parameters that we'll have in these very complex networks. Given a particular architecture that you're exploring, there are several sources of error that prevent you from fully modeling the real world. For example, there is an optimization error. That is, even if your neural network can perfectly model the world, your optimization algorithm may not be able to find the good weights that model that function. There's also estimation error. Even if we do find the best hypothesis, this best set of weights or parameters for our neural network that minimizes the training error, that doesn't mean necessarily that you'll be able to generalize to the testing set. For example, you might be overfitting, or you might be learning features that perform really well on the training and are actually reasonable to learn. For example, they might be very simple features or features that just tend to occur in your training set, but they don't generalize very well. You might also have modeling error. That is, given a particular neural network architecture, your actual model that represents the real world may not be in that space. For example, there may be no set of weights that model the real world. And so you can take a look at a simple neural network, for example, multi-class logistic regression. And you can think about here, we're actually using a very simple function. And so our modeling error is going to be pretty large. Clearly, the mapping between images to class labels can't be modeled by this simple function. And so there's no real set of weights within the space that we're exploring that can model this. If we use AlexNet instead, what would happen? For example, would our modeling error be larger or smaller? Since we're using a much more complex neural network with much higher capacity, our modeling error is probably going to be smaller. That is, our more complex function might be more likely to be able to fit this really complex function that models real natural images. However, we'll still have things like estimation error. Even if we find the best hypothesis that minimizes the training error, we may not be able to generalize. Because we have a lot of parameters, maybe we have a small amount of data and we'll overfit. And we may have optimization error. For example, because we made the neural network deeper, maybe the dynamics of our optimization will get more difficult to handle. Again, this is true of larger networks as well. Our modeling error will continue to get smaller because at some point we'll have so much capacity that we can probably model the true function that we're after. However, it may be that our optimization error will continue to increase. Or it may be that our estimation error will continue to increase because we're overfitting more and more and more, and we're not applying appropriate regularization. Again, all of the things that we have learned about, such as dropout regularization, batch normalization, residual networks, and so on, are all techniques designed to address some aspects of these sources of error. One question that always comes up is what if we don't have a lot of data? Again, we don't typically have a million labeled examples for all of our domains that we're interested in. In fact, getting that many examples is pretty expensive and time consuming. You need people to look at a million things, and actually, typically, you need multiple people to look at every data point in order to make sure that it's correct. And so one of the key surprises that came out early in the resurgence of deep learning is transfer learning. That is, we can reuse the features that we learned on a very large data set for completely new things. Here's how it works. The first step is we'll train on some large-scale data sets, such as ImageNet. That is, we'll take a very large convolutional neural network, optimize all of the parameters, both for the convolution layers as well as the fully connected layers. In the second step, we'll take our custom data set. Our data set may have different categories. It's not going to have the same 1,000 categories that ImageNet has. And so what we're going to do is we're going to initialize the network. So the parameters or weights that we use as initialization won't be from the methods that we talked about, such as Xavier. We'll just initialize it from the training that we've already done on ImageNet. However, because the last fully connected layer should be different because the number of classes might differ or the classes themselves differ, then we'll remove the last layer and just add a new layer. Here it's shown as a smaller one because maybe we have less classes. That part is initialized randomly. The final step is just to continue training from that initialization on your new dataset. So again, you initialize based on the weights that you learned on the large scale datasets such as ImageNet. But then you now train again using your dataset. This can be done in several ways. You can update all the parameters, just train as normal and update both the convolution filters as well as the last linear layers. Or you can freeze particular aspects or parts of the neural network. For example, you can decide to freeze all the convolution layers. What does freezing mean? Freezing means that you don't actually update those weights or parameters. And so you can just update the last fully connected layers instead. Why would you want to do this? This reduces the number of parameters that you need to learn given your new data set. If you only have a small amount of data, then maybe you don't have enough data to fine tune all of the features across all the convolution layers. Maybe you can just treat the large scale trained features as some fixed feature extractors that hopefully have relevant information because you trained it on a lot of other categories. And then you freeze it and then you only update the weights of the fully connected layers that depend on those features. This works extremely well, and these days seems very quaint because everybody does this, but actually was pretty surprising back when it was discovered. One of the key findings is that if you train a convolutional neural network on ImageNet, which has 1,000 categories and performs classification, you can actually apply that neural network to all sorts of different types of tasks. For example, here we show we can actually perform very small amount of data training on completely different types of things, such as scene recognition. For example, classifying whether a scene is a beach or indoors and so on. If you think about it, this might require very different features than classifying objects. But it turns out that using the features or the weights as initialization ends up doing extremely well when fine-tuned. And others have shown, and we'll see this later in the course as well, that we can actually also use these features, for example, that were trained for classification on completely different tasks. For example, object detection, where you're classifying tiny windows in an image rather than the entire image itself. Or even various forms of combinations of images and language. For example, image captioning, where given an image, we want to generate a sentence. The image features that we extract from this classification network are actually useful even for those kinds of tasks, which is pretty surprising. However, there are limitations. It's not magic. For example, this transfer learning approach does not work very well if the target task that has a new data set is very different. So for example, if we train a convolutional neural network on natural imagery, and then we want to apply it to things like sketches, where you just have a silhouette or a contour of an object, those features actually might be so different that maybe the initialization doesn't matter that much or won't help you that much. It also turns out that if you have enough data for the target domain, and it does have some difference from the source domain, then you might actually get better results by just training on the original target dataset itself with random initialization. This was shown recently in a paper that's cited here. Another interesting finding is that we still haven't reached a bottleneck in terms of amount of data if we do have it. That is, if we continue to add more and more data beyond the millions that we already have, performance continues to improve. And again, this is quite surprising. On the left, you see this from a Google blog. As we get to 300 million examples compared to the 1 million in ImageNet, our performance on object detection, as measured by a metric called mean average precision on the y-axis, continues to improve. And you could see this both for fine-tuning from ImageNet classifier or weights to no fine-tuning. In both cases, you get significant improvement. And the curve is still linear, and again, this is in a log scale, and so we know that more data will continue to help. We haven't reached the peak here. On the right, we can see some exploration where there is some irreducible error that we get to eventually, again in log scale. But this is only for a particular domain. What's interesting is that there are different regimes that were identified. For example, if you have too little data, then at some point it's very difficult to decrease the error. Then you enter a power law region where essentially the training dataset size in log scale continues to linearly improve the error again in log scale. And then again, at the end, you might get into some regime where you can't reduce the error further no matter how much data you get. But again, it's not clear that we've reached that for many of the interesting applications, such as computer vision or natural language processing. Finally, there's a lot of interesting research that's being done on the other end of the spectrum. That is, how far can we push in terms of reducing the number of labeled data? Unfortunately, in this field, there's a lot of different settings. So we have semi-supervised learning, where we have a single labeled data set and a single unlabeled data set. And typically, the amount of labeled data is much less than the unlabeled data. But there's no shift between the two. By shift, I mean there's no distributional difference from a probabilistic definition. There are different types of shift, actually. You can have non-semantic shift shown on the lower left. For example, you can have a sketch of a bird or a natural image of a bird. You can also have semantic shift, that is shown on the lower right. You can have both images, but images of different things. And so there's a whole range of different types of machine learning settings that people have looked at. Domain adaptation, for example, looks at if you have a single labeled data set and a single unlabeled target data set, but there's no semantic shift. That is, the label space is the same, you have the same categories, but you might have some type of non-semantic shift. That is, you might go from natural world images to sketches. You might also have what's called few-shot learning, where you have only one example or maybe three examples, and you're learning to generalize from a very large data set with many categories and many labeled examples, all the way to a new data set that has completely new types of objects, but you only have 1 to 3 examples per category. And this is the same again for a bunch of other different types of settings. And a lot of these are still in the research stage where it's not clear how to get the best performance across these settings. However, very significant performance gains have been made in the past few years. For example, in semi-supervised learning, you can often get very small degradation in accuracy with only 5 to 10% of the data, which is pretty impressive. And as the research progresses, I'm sure many of these settings will become much improved. In this lesson, we'll learn about a new type of layer called a convolution layer. Unlike a fully connected layer, convolution layers will not be fully connected to their inputs. And we'll see why this is important for various modalities such as images. We'll talk about what convolutions are and how we can easily implement them in deep neural networks. Backpropagation and automatic differentiation allows us to optimize any function composed of differential blocks. There's no need to modify the underlying algorithm dependent on what the blocks are. And the complexity of the function is only limited by computation and memory. This is really the power of deep learning. However, different types of layers are appropriate for different types of input data. And the fully connected layer, which has a very specific connectivity pattern where each output node is connected to each input node, is not necessarily the best for every type of application. Take images, for example. Suppose that an image has 1024 by 1024 pixels. When we convert this to a vector, we'll roughly have a million elements. If we put a fully connected layer right after it with n nodes, let's say n equals to 1,000, how many parameters or weights will we have to learn for this layer? If you calculate it, you'll have m times n weights plus n biases. That is one bias value for each output. If m is a million and n is 1,000, you'll have lots and lots of parameters. So you can have hundreds of millions or billions of parameters for just one layer. In deep learning, we can continue to add more and more layers together. And there are several issues in machine learning with having so many parameters. For example, the more parameters or weights that you have to optimize or learn, the more data you need to actually be able to fit all those values. That is, your model has an extreme amount of flexibility, actually too much flexibility that it doesn't actually need. And you need lots of data to fit that flexibility and make sure that you don't overfit. And so there's a question that we can ask ourselves. Is this really necessary? For example, for images. Images in particular have special characteristics that make fully connected layers not as applicable and allow us to do better in a more parameter efficient manner. Specifically, image features are spatially localized. For example, take edges or contours. As you can see on the image to the right, they're very informative. You can already see that this is a bird even without seeing the pixel intensities on the image to the left. And so what we'll have is features such as edges that we can actually extract not by looking at the entire image, but looking at small image patches. For example, given a small image patch, we can detect whether there's a gradient. And this is not a deep learning gradient, but a differential between the pixels. There are dark pixels on the left and light pixels on the right, or vice versa. And those tell us whether there are edges in this little image patch. And we can repeat this across the entire image to extract features such as edges. This is well known in areas such as image processing. And so there's smaller features that are repeated across the image, and edges are one example, but other examples include color or even things like motifs such as corners or small circular shapes and things like that. Any local feature that you can extract or detect by just looking at small image patches, not the entire image itself. If you think about it, fully connected layers, each node looks at all pixels in the entire image, and this may seem silly. Further, there's no reason to believe that one feature tends to appear in one location versus another. For example, if you just take a natural image anywhere in the world, there's no reason to believe a beak might appear specifically only in the middle of the picture or only to the upper left. Now, you might have small image collections that have biases in locations, but in general, over all possible images, there's no reason to believe these local features are going to appear somewhere in the image specifically. In other words, the feature extractors do not have to be location specific. And so we can use these properties to induce a bias in the design of the neural network layer to reflect this. And by bias, I mean that we'll explore specific connectivity patterns that are more appropriate to images and that will reduce the number of parameters that these layers will have. Specifically, what we'll do is have each node in the neural network, rather than take inputs from the entire image, we'll take inputs from just a small, what we call receptive field, or small window or image patch in the image. For example, it'll receive input from a K1 by K2 window on the upper left. And so this node will output the existence of a particular type of feature in that little window, for example, an edge. The advantages to this is that the number of parameters will be reduced to K1 times K2 plus 1 for a bias element times n, where n is the number of output nodes. And so we can toggle this. We can control the number of output nodes, and this will allow us to have only a certain number of output nodes, each of which only takes input from K1 by K2 image patches. Again, the key idea here is to reduce the number of parameters. It's no longer m times n. It's a smaller window, k1 by k2 times n, roughly. And one interesting thing about this way of doing things is that it also maintains spatial information. Now, a fully connected layer can maintain spatial information because each node takes input from the entire image, and it can, for example, weight any parts of the image up or down. And so it can try to maintain some elements of spatial information. But here, we're actually going to organize the output nodes also spatially, such that they're explicitly maintaining this information. And we can even do better. We can think about the fact that I mentioned before in terms of features not existing in particular location. Do we really need to learn a node that extracts specific types of features as represented by the weights, the K1 times K2 weights, in a particular location in the image? And the answer is no. What we can have is nodes in different locations sharing features or weights. Weight sharing means that the specific weights, for example, W11 for the leftmost node is going to be the same as W11 for the rightmost node. The way you can accomplish this is by just having the same variable in the computation graph feed into both of these nodes. And so we'll have several nodes across the entire output all share weights. Now, what is this intuitively doing? Intuitively, the weights will represent some sets of features that we extract. And what we'll do is we'll share those features across all the nodes. That is, we'll try to, let's say, have an edge detection feature, and that edge detection feature will be run across the entire image because each node will run that same feature across the entire image. And so again, we're using the same weights or parameters in the computation graph. This is called shared weight. Again, the advantage here is to further reduce the number of parameters. Now we don't have this factor of n, the number of output nodes. If we just want to extract one type of feature, we'll only have k1 by k2 plus 1 parameters, and we'll run this feature extractor across the entire image. And again, we're still explicitly maintaining spatial information. And so now we've gone from m times n weights all the way down to a small number of weights, k1 times k2. So for example, if this is a 3 by 3 window, we'll literally only have 3 times 3 plus the bias term, so 10 parameters. And we can also learn many of these features. So we may not want to be limited to one type of feature. Obviously, we can have vertical edges or horizontal edges or lots of things in between. And we, at the same time, also want to represent different color features or texture features or corner features or other shapes. And so we will want to have multiple types of features. So we'll have one channel of output, for example, on the upper left, that represents locations of features, for example, let's say edges or a particular edge orientation. And so this output channel will have nodes with high values in the locations that have such features very strongly. And then on the lower left, we'll have another channel of output that represents the location of a different feature. And so across the different types of features, the weights are not shared. We'll see in later slides that the weights themselves will represent what types of features we extract from these little windows. And so we want them to not be shared across different types of features. But for one particular type of feature on the upper left, let's say all of the nodes are sharing their weights. That is, they're extracting the same type of feature over different locations in the image. And so the number of parameters now, we've increased it a little bit, but we've also increased the expressiveness or representational power. That is, now we can represent multiple types of features. And we'll have k1 times k2 plus 1 times m features or parameters, where m is the number of features we want to learn. And so now we want to understand how can we actually implement this feature extractor. We've talked at a high level about feature extraction, but how can we actually implement this mathematically? If you have an electrical and computer engineering background, what we described, that is some filter or feature extractor striding along an image and outputting values that are high if it picks up a particular type of feature, may sound familiar. This is actually called a convolution operation. And it's extremely common in various fields of study, including electrical engineering and so on. And it has a lot of deep mathematics behind it, some of which we won't really cover. And it's also related to something called cross-correlation, which we'll also discuss. But it has a whole wide range of applications. And so really the reason we frame this as a convolution operation stems from the history of where this type of layer came from. So what is a convolution? In mathematics and electrical and computer engineering, there's actually continuous forms of convolution operations that we won't go into. And there's also lower dimensional convolutions, such as 1D discrete convolutions. Again, we're not really going to talk about these because we're describing image processing here, and so we'll deal mostly with 2D convolutions, although later we may talk about 3D convolutions and extensions. Now, a 2D convolution in particular looks like this. We will have an image that is fed through what's called a kernel or a filter. And we will perform a convolution, that is, we'll convolve the image with this kernel, and we'll get what's called an output or filter map. Sometimes it's called a feature map, and in deep neural networks, it's called an activation map. In any case, it represents the same thing. The output is spatially relevant and maintains spatial information of where the particular kernel or filter is highly expressed in the original image. So here you can kind of see a pattern to this particular kernel we have here if we visualize it in grayscale, where dark values are very low negative values and light values are high value positive values. You can see that this kind of looks like an edge. And this is not a coincidence. What we'll have is this filter will be convolved with image patches, so portions of the image. And if portions of the image have very dark locations on one side and very light locations on the other side, this filter will activate very highly. And so you'll have very high values in the corresponding region in the output map. In deep learning, we'll make this convolution operation a layer. That is, we'll have some input, say an image, and we'll perform some function on it, some linear function in this case, and we'll have an output. And so what we'll actually learn is the kernel or filter itself. That is, these values where you see -1, -2, and -1, and so on, will actually initialize randomly to small random values. And then we're going to backpropagate through this layer in order to optimize this filter such that the output maps after this operation will allow us to, for example, classify what's in the image. Now, there's a very mathematical way to describe convolutions, and we'll get to those. But let's describe the intuitive interpretation. What we're actually going to be doing is very simple. We're going to be taking the kernel and flipping it or rotating it by 180 degrees. This is depicted here in the slide. And then all we're going to do is we're going to essentially dot product that kernel with all the different image patches or locations in the image. That is, we'll start from the upper left and we'll take a dot product between the 9 values in the upper left of the image and the kernel. And so again, we're just multiplying, let's say, the upper left of the image pixel multiplied by the upper left of the kernel, and so on, and do this for 9 of the values. And then we'll also add a bias term later. And this dot product will result in the value output of the first pixel in the output map, depicted as that white circle here. Now, you'll notice that we'll do this over and over again over all locations in the image, but at some point we'll run out of room. That is, for example, if we move 1, 2, 3 over in the image, then at some point the filter will go off the image. And so that's why there are blanks in the output map. That is, the output map size is going to be slightly smaller because as we move the filter over the image, we start to go off the image. And at that point, we won't actually produce an output. So this is the intuitive way that we'll describe a convolution. We'll just take a kernel, we'll flip it or rotate it 180 degrees, and then stride it along the image, just dot producting the kernel with that image patch and producing an output. Now, even though that description of what we're doing in the convolution operation is pretty simple, mathematically describing it gets a little bit hairy. And that's because we need to define coordinate systems for the image and the kernel and somehow describe mathematically this operation of flipping the kernel as well as striding it over the image. Suppose that we take the image here, simplified into a 5x5 grid, and we'll represent a coordinate system where the center pixel is 0, 0. And so the upper left is going to be negative height minus 1 over 2, comma, negative width minus 1 over 2. And then the lower right will be the positive version of that. The kernel's coordinate system will be a little bit different. We'll have the upper left defined as 0, 0, and the lower right defined as k1 minus 1, comma, k2 minus 1. And so let's look at the equation that describes how to perform this convolution operation. So again, it's a little bit hairy because of the coordinate system issue. But let's take the output map y. So y represents our output, and r comma c will represent the pixels that are in the output. So r represents the row, and c represents the column. And so 0, 0 is going to be on the upper left in this case. what we're going to do is y of, let's say, 0, comma 0 will equal to the summation over the entire image, where we dot product or multiply the input pixel, the image pixel, times the kernel value. But if you look, we're summing over from upper left to lower right all the pixels in the image, and we're multiplying x of a comma b. So a is the current pixel in the image, and b is the current pixel in the image. Again, this is the input image. R comma C is on the output image. And we're multiplying pixel A comma B in the input image with the kernel value. But the kernel value is not A comma B. It's actually R minus A and C minus B. And this is actually what is representing mathematically that operation of flipping the kernel. Let's take a look at an example. Let's say y of 0, comma 0. What we're going to do is iterate over all the pixels in the image, in the input image. And so this includes, let's say, on the upper left, which is x of -2, comma -2. And so now a equals -2, b equals -2. And again, because we're looking at y of 0, comma 0, r equals 0 and c equals 0. So if you work it out, the actual kernel pixel that we're multiplying it by is r minus a, which is 0 minus -2, which is 2. And the same for the second coordinate. And so we're multiplying x of -2, comma -2, again, the complete upper left pixel in the image, with k of 2, comma 2, which is actually the lower right of the kernel. And this is actually what's representing the flipping operation. And so if you look, these lines show that we're directly multiplying the pixel image on the upper left with the kernel value on the lower right, and that gets to contribute to the y of 0, comma 0. Now that's just the first pixel. We also have x of -2, comma -1. And again, we're actually, in this case, multiplying it by k of 2, comma 1, and so on. Now, if you notice, at some point, you'll have negative values for the kernel. And of course, you can't actually have that. There's no value there. And so we actually just throw those values away. And so if you kind of work it out mathematically, we're actually doing what I intuitively described. We're multiplying the flipped kernel by just that upper left 9 by 9 set of values. And so again, you can work this out, and you should spend some time to see how it all works out. But that's essentially what this mathematics is describing. And again, just to reiterate, as we're moving from the upper left to the lower right in the image, we're actually multiplying at each point in the input image by this flipped kernel, because we're going from the lower right in the kernel to the upper left in the kernel. Now, this is pretty confusing, and so you can actually try to make this a little bit less hairy by, rather than centering around the image, you can center around the kernel itself. So here, we've changed the summations to iterate over the kernel. And now, again, the only difference is that if you notice, it's the x values, that is, the values in the input image, are the ones that have this r minus a and r minus b. And so, as we've seen, we're actually taking the convolution operation and starting at the end of the kernel, that is the lower right, and moving backwards towards 0, comma 0. And this is, again, intuitively described as a flipping operation. And it turns out that convolution has a relationship with another operation called the cross correlation. The cross correlation is actually very similar to convolution, except it's applied with the flipped kernel. And we're doing exactly what we described, which is we're taking the flipped kernel, and cross correlation just takes the dot product of each image patch with the kernel and produces an output. And so again, there's an intuitive interpretation in that essentially the convolution and the cross correlation are very related. And really the cross correlation is only different in that it's flipping the kernel from the convolution and then applying the normal dot product operation that we've talked about. So again, you take the kernel, you rotate it 180 degrees, you perform this cross correlation, which is just essentially this dot product as you stride it along the image, and then you add up all those values to produce the output for each pixel. And so this is the mathematics of cross correlation. It's actually a little bit nicer because if you notice, rather than having this weird r minus a, we're now adding things, which is a lot more intuitive. And we can have the coordinate systems be the same for both the image and the kernel. So specifically for the image, we have the coordinate system be 0, 0 on the upper left and h minus 1, comma w minus 1 on the lower right. And the same thing for the kernel. And so again, if you go through the math of this, essentially all you're doing is taking that kernel, which is now the flipped kernel from the convolution, and we're applying it at each location in the image, dot producting that kernel, and then producing the output. Now, one interesting thing is that essentially, again, now the pixels are moving in the same direction. That is, the indexing is moving in the same direction, which makes things a lot more intuitive. And we'll see this make the backprop equations much simpler. One interesting thing is that since we're learning these kernels anyway, essentially those kernel values are going to be randomly initialized and some learned thing that gradient descent tells us to optimize to. It doesn't really matter whether you flip the kernel or not. And so really, with respect to a learned kernel, there's no real difference between convolution and cross-correlation. And so let's take a concrete example here, just with actual values. So let's say that our upper left 9 pixels, so that is x of 0 to 2, comma 0 to 2, have these 9 values. And I completely made these up. And let's say you're dot producting them with the kernel k prime. That is the flipped kernel. And so this is just one example of a kernel. This is kind of an edge detector called a Sobel filter, if you're curious. And so the dot product will essentially be 200 times 1 plus 150 times 0 plus 150 times -1, and so on for all 9 values. And then we'll get the result 65. So this is just a concrete example of the dot product. And typically, as I mentioned, you'll also have a bias value similar to all the other linear layers that we talked about before. And again, we're just going to do this and then stride it along the image. So there's a question in that some of this may seem confusing as to why we're actually going through the notion of describing what a convolution operation is and describing everything mathematically. And at the end, all we get is just another linear operation. Actually, it's very similar to W transpose X, except the only difference is that our W is going to be a small window, and we're going to do W transpose X across the whole image. We're going to stride that W across the whole image to get a spatially organized output. And so why are we bothering with all this mathematical formulation of what a convolution is, as well as describing the relationship between a convolution and a cross-correlation? The first reason is that there's actually a duality between cross-correlation and convolution. It turns out that when you do the forward pass as a cross-correlation, which is actually how we'll implement it, because that's the easy thing to implement and it's also easy to vectorize. It turns out that when we compute the gradients, which we'll go through, it actually will be a convolution. And actually, if you do a forward pass as a convolution, the backwards pass will be a cross-correlation. So it's good to know the relationship just because of that. Also, convolutions have various mathematical properties that researchers care about. And so there's a whole rich set of electrical and computer engineering body of literature that has analyzed convolution operations. And so if we relate these layers to those, then maybe we can analyze them. For example, we can take the kernels that are learned when we do cross-correlation, and we can then flip them and describe them as a convolution and maybe do some analysis. Also, this is historically how it was developed. The researchers that developed these had rich image processing backgrounds, and so really they thought of these layers as a convolution operation, and so that's how these things are also described across the entire literature. So it's important to know that actually when we describe a convolutional neural network or a convolutional layer, it turns out that that's not actually what we implement a cross-correlation, and it's good to know this if people ask. In this lesson, we'll describe the input and output sizes of a convolution layer and the various design decisions that can be made for these layers. A convolution layer, as we described, is taking a kernel of a particular size and striding it over the image and doing a dot product across all the locations to produce a spatially organized output map. Now, there are several design decisions or hyperparameters that exist for these layers. This is showing specifically the output of a PyTorch documentation. For example, we have the input size, that is the width and height, but also how many channels. For example, in an image, we may have 3 channels, red, green, and blue. And then we'll have how many output channels. And we'll see this is actually equivalent to the number of kernels that we'll use. We'll also have the kernel size. We can have 3 by 3 as we've shown, but you can also have 5 by 5, 6 by 6, or really any size that you want. They don't have to be square either. We can also have the stride, that is, we'll move the kernel along the image, not 1 pixel at a time, but a few pixels at a time. We can also have padding. As we'll see, we can pad the image or surround it by zeros, for example, in order to change the output size. So let's take a look at the output size first. The output size of a vanilla convolution operation is just the dimension of the image minus the dimension of the kernel plus 1. So for example, the height of the output will be the height of the image, here 5, minus the height of the kernel, in this case 3. So 5 minus 3 is 2, plus 1, which is 3. And so here you can see, since we have square inputs and square kernels, we'll have the same square output as well. So we'll have a 3 by 3 output map. Again, the reason it's smaller is because if we move that kernel over more than 3 times, for example, the 4th time, then the kernel goes off the image. And so that's not a valid convolution. And so a valid convolution is only when the kernel is fully on the image. We can also pad the image to make the output the same size. In some cases, we want to have one input size and then have the same output size. And so what we can do is just surround the image, for example, with zeros. But there's lots of other things we can do. We can mirror the image. So for example, the pixels at the border will be reflective of the pixels in the actual image across the border. And note that padding often refers to adding one dimension. So p equals 1, or padding size of 1 here is shown, but actually you're adding 2 to the height because you're going to add a padding to the bottom as well as to the top. We can also, again, move the filter along in larger step sizes than just 1. This is called the stride. One interesting thing is that this can potentially result in loss of information. For example, if your kernel size is size 3 by 3 and you're striding across 6 values, that is, you're taking the kernel on the upper left of the image and then you're going to skip 6 pixels to the right to get the next one, then you're actually going to skip pixels. And so you can actually have some loss of information and you can have dimensionality reduction as well. So you don't necessarily have to skip pixels. For example, if you have a 3 by 3 and you're moving by 2, you actually are still not skipping pixels, but you do have a smaller output on the output side. And so again, this is just one way that you can do dimensionality reduction. Typically, this is not actually the best way to do it. We'll see other better ways because, for example, you don't want to lose information. Note that some combinations are not going to be valid and can result in skip pixels at the edge. So for example, if you're taking a 5 by 5 input and you're striding a kernel of size 3 by 3 every 3 pixels, then actually the last time you stride the kernel, it'll fly off the image. And so really here, you'll only have 1 pixel that's a valid pixel in the convolution if you're doing valid convolutions with no padding. And so again, that could result in skip pixels. So you really have to make sure to account for edge effects here. So far, we've talked about one-channel inputs, such as grayscale images. But in reality, images have 3 channels, red, green, and blue. And so we'll have a tensor of size, height by width by 3. And so there's a question of how to apply the convolution operation. It turns out we can just have a 3-channel kernel. That is, we'll have the depth of the kernel extended to be equal to the depth of the input. So if we have a K1 by K2 kernel, we'll now have a K1 by K2 by 3 kernel. And what we'll actually do is the same dot product operation, except rather than do it with 3 by 3 values, that is 9 values, we'll do it with 3 by 3 by 3 values, that is 27 values, if the kernel size K1 is 3 and K2 is 3. So this depicts how you can do this. Essentially, again, you're just dot producting the kernel with the image patch, except you're doing it by summing up the contributions across the depth as well. There's different interpretations. You can, for example, just see this as doing 3 kernels that you essentially dot product with the 3 channels of the input image, and then you sum them up spatially. That is, you take, let's say, pixel 0, 0 of the 3 outputs that you'll have for the 3 kernels that are single channel, and then summing them up. We can also have multiple kernels per layer. Again, we want multiple feature extractors for each image. And so if these kernels represent things like edges of a particular orientation, we'll want to have many of them. And then we'll also want ones that represent extraction of color features or texture features and so on. Again, we're not really enforcing what features they'll extract. All we're doing is randomly initializing it and hoping that gradient descent will essentially learn different features. This is a question that's actually pretty common. There's a question of why you won't learn the same exact types of features. So why do you think that is? And it turns out that the reason is that we'll initialize them to different values. So all of these kernels will initialize to different values, and their local minima in their local weight space will be different. And so they'll end up learning different features. The gradients for each kernel will be different because we initialize them differently, and they'll move in different directions. Now, that doesn't mean that you might not have redundancy. You actually will, and we'll see this when we actually visualize what this network will learn. So in summary, we'll essentially have many different kernels, and each kernel output will be of channel 1. And so the number of output channels, which will combine by just putting them together, concatenating together, will actually just be the number of kernels. So here we have 4 kernels, and so the output map will be of depth 4. And again, the height and width will be the same calculations as before. So this is the key thing to remember. The number of channels in the output map is equal to the number of kernels that we have. Now let's take a look at the number of parameters. If you remember, this was the reason we did this whole exercise. We wanted to reduce the number of parameters. And so for each filter, let's say in this case, K1 by K2 by 3, that's how many parameters we'll have, because each of those values in the kernel is the parameter that we're learning and that we initialize randomly. And if you notice, we'll have a +1 here, again, for the bias. Each kernel will have a bias that the output will be offset by. And so let's say we have n kernels, we'll have n times k1 times k2 times 3 plus 1 values or parameters. And so as an example, if k1 equals 3 and k2 equals 3, and we have 4 of them, then our input channels are 3 and our output channels will be 4. And the number of parameters we'll have is 3 times 3 times 3, which is 27, plus 1, which is 28. And then we multiply that by 4 because we have 4 kernels. And so the total will be 112. So that's how many parameters we're optimizing using gradient descent. Just as with any other layer, we'll want to vectorize the operation that we want to perform. This is because specialized processors, such as graphics processing units, are really good at these linear algebra operations. And so rather than take the image patches and do a for loop around them in order to apply the kernels, what we're going to do is we're going to take the image patches in the image and vectorize them. So each image patch will be converted to a vector, and this can be done even if it's a multi-channel image, as long as you keep the ordering the same. And then you'll lay them out as rows in a matrix. And then we'll just take the kernels and also lay them out in a different way as a matrix. And we'll just perform the whole operation as a matrix to matrix multiplication. That is, in the first matrix, we'll have the image patches along the rows. And in the second matrix, we'll have the kernels along the columns. And then we'll just multiply them together. If you notice, this applies the same kernel 1 to all the image patches, which is again what we do in this weight sharing scheme. And that's the key to the convolution operation. And this kernel matrix is all learned. All of these values will have initialization of random values, and then they'll be optimized through gradient descent. And because we're applying the same kernel to all the image patches, this is equivalent to essentially doing weight sharing. That is, learning a feature that has the same weights and is applied to all the image patches. In this lesson, we'll talk about a different type of layer called a pooling layer that can perform dimensionality reduction, that is, downsampling things like images. Dimensionality reduction is an important aspect of machine learning. As we know, we have very high dimensional inputs, and we often don't actually need to characterize those high dimensional inputs in as much information. That is, we can compactly represent the important information, for example, for the task of classifying what's in the image. And so there's a question of whether we can make explicitly a layer that downsamples images. And the answer is, of course, yes. Again, there's nothing preventing us from applying many types of different types of differentiable functions. And so again, we show this PyTorch definition where we can see actually the same types of hyperparameters as the convolution operation, as we'll see. And so we can have a layer, for example, called a max pooling layer. Here, we're going to stride a window across the image, very similar to how we did convolution. Except rather than perform the convolution operation, we'll just perform the max operation. So for example, we'll take a window 3 by 3 and take those 9 pixels and perform the max, and that will be the first pixel of the output map. Here's an example, again, with made-up numbers where x of 0 to 2, comma 0 to 2 has these values. Then we just do a max, and we just have an output of 200. So how many learned parameters does this layer have? And the answer is none. This is just the max operation. It actually doesn't have an argument other than the things that you're doing the max over, but there are no parameters W that we need to learn for this layer. So this is strictly a max layer that is striding across the image. Now, of course, you're not restricted to a maximum. You can use any differentiable function. So for example, you can apply the average pooling where you're averaging all the 9 pixels here to get one new output pixel. Now, this is actually not very common in practice. Typically, we use max operation, and actually, you'll see in much later neural network architectures, we actually might get rid of the pooling layer altogether and perform dimensionality reduction, for example, using convolutions themselves. Since the output of a convolution and pooling layer are just multi-channel images, that is tensors of size, width, and height by depth, we can actually just sequence them together, just like any other layer. For example, we can take an image, perform a convolution operation, in this case just one kernel, get an output channel or image, and then we can apply pooling to that same output. And so we can just continue to sequence these together over and over again. Now, it turns out that this combination, where we perform a convolution and then a pooling, actually has a powerful feature. Specifically, it results in what's called invariance. That is, if the feature, for example, a beak, translates or moves a little bit in the image, the output value may still remain the same. This is because the kernel, for example, the feature that picks out beaks, will have a high value that moves a little bit in the output map. But if we move within the pooling window, that is, as long as the movement is not much larger than the size of the pooling window, then the max across that window will still be the same. And so if there's a high value there because there was a beak there, then we'll still, after pooling, have a high value. And so movements, at least slight movements, of the features themselves in the input image will result in the same exact value in the output map. This is what's called invariance. Now, we can also have something called equivariance, and this is something that convolution operations naturally have even without pooling. That is, if the feature, such as a beak, gets translated a little bit, then the output values may move by the same translation or transformation. So specifically, if the beak feature or pixels move a little bit, then the kernel will still stride across the entire image and pick it up in that new location. And so it'll have a high output value in that new location. And so this means that in the output map, the high value moves in the same direction as the actual feature in the image. Again, this is called equivariant. And both of these types of features are actually quite important. For example, in terms of invariance, we want various transformations or things like translation or rotation to not affect the output very much. Eventually, at least deep in the network, when we start to do classification, we don't want the classification outputs to change very much. We still want this bird to be classified as a bird, even though the beak feature moves. And so having these equivariance and invariance properties are actually very important.